Okay, great. Yeah, so the recording has started. So, we're just basically going to build up from what we discussed yesterday. So, let's look at this question. So, interactive example 18.3. So, consider the galvanic cell based on the reaction. Uh, so, actually, okay, let's do this. So, the reaction of interest is what? The reaction of interest is aluminium aluminium, then we've got magnesium, and then they form solid aluminium and magnesium ions. So you are given that equation, and then you are told uh, give us what the give us the balanced cell reaction, and then also calculate the E for this particular cell. So what you're going to do first of all is you want to look at you know, look at the reactions, or rather look at which one is being oxidized and which one is being reduced, right? So from this you can tell that aluminium is being reduced, okay, and you can see that the magnesium is being oxidized, isn't it? So now what we write then is we know that magnesium is being what? Magnesium is being oxidized, okay? So we know that magnesium is being oxidized, okay? So to balance the electrons, we do that. Now, we know that all our standard electron potentials, they are always taken from reduction concept, right? So meaning that like this one for magnesium, it's actually taken from the concept of what? Of reduction. So meaning those standard E values that we'll be looking at, by what I mean, we discussed this yesterday, but this simply means that those values which we will be using in those tables, they are gotten from a situation like this. All right, and so the E is going to be what? So the standard E, that's all there on top. So the standard E is going to be what? Negative 2.37 volts. So that's what you are seeing there. So now we know that in this case it's being oxidized. So meaning this has been rotated, or rather this has been reversed, okay? So it means that this reaction has what? Has been reversed. So if it's been reversed, what it simply means that, remember, when you reverse the equation, the value of E, you multiply it by what? By negative 1, right? So you multiply it by negative 1. So meaning that what you are getting is your you could call it your negative E now. So but anyway, let's not make things complicated. So just know that your E has what? Has been reversed, and it's now what? Positive 2.37 what? Volts. Okay, so I hope that makes sense. So there we have it. And where does this happen? This happens at our anode. That's where oxidation happens from. So we know that's our anode. So if we already have an anode, then we know that the other one is going to be a what? It's going to be the cathode. So this reduction, it's going to be at the cathode. So it's going to be aluminium like that, right? So if you want, you can put state symbols there. But yeah, so now you want to balance the equation. How do you balance the equations? Here you see that the elements themselves are balanced, right? Like in terms of atoms. So you are balancing the charges, or rather the electrons. So you multiply. How can which elect what numbers can you multiply to ensure that the electrons being transferred are the same. So what you do is you multiply the first one by 3 so that the electrons will be 6. Then to make 6 for the other second reaction, you multiply by 2, right? When you multiply the 3 electrons by 2, that's when you're going to get what? That's when you're going to get 6 electrons, which then is going to be 3 magnesium. Then you're going to have 3 magnesium ion and 6 electrons, right? And then you're also going to have for the reduct. Oh, then let me put the E for the cathode. So the E for the cathode, it's negative. It's negative 1.66 that. Okay. So because for this particular cell, it's already been put, so there is nothing like saying no, the one which is more positive is the one that occurs when you are being asked to say how will these arrange. But this one, they've already given us the reaction, so we just take them as they are. Okay. But again, if even if you use that token, you would still see that this same one, the one that's the cathode, it's less negative, because remember that this one, the magnesium, was what? Was negative 2.37. So again, either way, our principle still holds true. Okay, our principle still holds true. So then we say that, then you say that, so that's going to be 6 electrons, then that's going to be 2 aluminium, right? So we cancel the electrons, then we just write what remains. So let me use blue so we can be able to differentiate these. Plus, write that properly. So there you're going to have that, then you're going to have 2ls, then you're going to have, yeah, so that's basically that. But so you've written, you've pretty much balance the equation. Then now we want to find out the E. So remember our E for the cell is going to be what? Cathode is for the E of the cathode. E for the cathode minus the E for the anode. So what you're going to do, what's your cathode? Your cathode is negative that. Okay, then now what you're going to put here, so yeah, so once you've done that, I think this was the question that someone was asking yesterday, to say how do we know what to put. So now get this trick, right? If we write this particular equation the way it is, negative, and then we write what the E for the anode is, it's like that. Okay, so it's going to be like that. And then also using the, okay, so voltage, then using the method that the person was telling us yesterday about, it's going to be the same thing, where we say we are adding the two E's. So you say E cathode, E for the cathode, plus E for the anode. So you say this is going to be negative that, then what's your E? Your E is positive, right? So you're adding, so it's going to be positive that. So it just depends on which preference you have. But yeah, both works. What's just important is understand the concept and that, right? So that's pretty much about it. So now, yeah, I think that's really exhaustive on those kinds of questions. Now let's now talk about the line notation. So what's the line notation? The line notation, this is a simplified way of representing a galvanic cell. Okay, so how you do this? Let's look at first. Let's look at figure 18.31. Okay, 18.31. Okay, let's see which one is figure 18. So figure 18.3. Sorry, 18.3. 18.3. Okay. Anyway, so figure 18.3, the cell that we are looking at there, it's oh sorry, not figure, in example 18.3. So you see example 18.3a, that's the question that we are from doing, right? So we see that we can write the line notation in this format. So what's going to be okay, so what's important to take note of is this: what is on the left. Okay, or maybe let's write it like, let's start the line notation from scratch. So the line notation is going to vary depending on whether you've got platinum as one of your electrodes or not. Remember, you're going to have platinum as one of your electrodes if the components that are reacting, there is nothing that can really, there is no metal that can act as an electrode. Okay, so in that particular context, what you're going to have is you're going to use you're going to use a platinum as your electrode, right? So now for what we are from looking at, okay, from what we are just from looking at this particular cell that we are from looking at, we realize that um our okay, so the reaction was this, for the sake of, okay, let's just put the state symbols. So that's AQ. Let me write it properly. So that's aluminium, that's AQ. Then that's going to be magnesium. Then you're going to have aluminium. Then you're going to have magnesium. So what then is going to happen here is, when you're drawing the line notation, so what's going to happen is you're going to have that, you're going to have that, then you're going to have that. So let's now discuss these two lines. Okay, those double lines, what do they represent? They represent what you would call the salt bridge or the porous disk. Remember those, the salt bridge that we were talking about yesterday? So that's what these, so you can remember, you can either use a salt bridge or you can use a porous disk, okay, to separate the cathode from the anode, or the other way around. So you use that, right? Oh, sorry, not to separate, but to balance the charges. Sorry, to balance the charges between the cathode and the anode. Okay, so that, so those double lines there, they are representing the salt bridge. And then let's now go to the left. Everything on the left is for the anode. So the question then you have to ask yourself is, what happens at the anode? We know what happens at the anode is what? Is oxidation. Okay? And so if it's oxidation, then we are having a picture of, we know that it was magnesium which was being oxidized, right? So we have something like that, right? So what this simply tells us is, you've seen this single line. What this single line represents is the change in phases. Okay, so that single line there represents the what? The change in phases. So you see that This was solid, now it's in aqueous solution, right? So there's been a change in phase. So you write them in the exact way that they are. So what's going to be on first part is going to be what? This one. So that's the one that comes first on your line notation. So let's come here and write it like this. So meaning you're going to have what? Magnesium, that. Then that line showing that now, even though it's the anode, but there's been a change in phases, right? So you're now going to have this one which has been formed on this side, right? And you're putting the state symbols, right? Then once you are done with the anode, what comes after the anode? Before you got the cathode, there is a salt bridge or a porous disc. You get it, right? So after you've done that, then meaning that you've now left the what? You've now left the anode, and you're now looking at the cathode. Now, what do we have as the cathode? Using the same example that we've already explored so far, what we are going to do then is we are going to say what's being reduced in this example. So, you know what's being reduced in this example is what? Oh no, sorry, I made a mistake. This should be aluminium plus 3, yeah? Okay, so aluminium is what's being reduced like that. So here we know it's aqueous solution. Then there it's that, right? So how? So again, we know that that single line on the right, we are now talking about the what? We are talking about the cathode, because you know that that's where your what? That's where your reduction is occurring. So again, now how are you going to write them? So you write them starting with what happened first. So you see what's happening first. It's this one that's present first. So that's why here you're going to write it. So you're going to write it first, and then your state symbols. Then this line representing that it has now changed the phase. It's now from aqueous to now solid. So you write then what comes later on is what is this solid, right? Okay, so you have that. Then you are done. That's your line notation. Okay, so that's how you write a line notation. Now, so that's an example where both electrodes they've got metals which can serve as electrodes, right? But then you're going to have those others where it can't serve as an electrode. So what you're going to do for these ones, that's where now your what's this is going to be a little bit unique. Okay, your line notation is going to be somewhat unique. Not hard, but just unique. So let's look at the example that we have in in example 18.3b. So this was the example which was there. So they have reactions. Yeah, so just look at that example there on top before the line notation part. So they have reactions there. It has already been reduced, so you can see what's happening there. So you see that for this particular reaction, the ions that you are having, so the ions that you are having, you see that let's first look at the cathode one. There is nothing that can serve as a metal there. Okay, there's nothing that can serve as, sorry, there is no metal that can serve as an electrode. Yeah, let me put it in the best way there. So there is nothing there that can serve as a what? That can serve as an electrode. So what then happens? It means that, so sometimes for certain reactions, it may just be maybe the anode that doesn't have a metal to serve as an electrode. Sometimes like this reaction, it can be both the anode and the cathode, right? So what you use, the same way we did it for hydrogen. In this case, you use platinum. Okay, so you're going to use what? You're going to use platinum. Platinum is going to be your electrode. So you have to write the platinum as well. You want to write the platinum as well. So for this particular equation, so let's write the equation, I guess, so that we are going to have a good picture. Let's just write it down so that we can be able to derive this together. So otherwise, that's really about it. So let's now write this equation. So now this particular equation, what we are taking note of is that is this for the cathode we are having. So for the cathode we are having, so okay, let's do it like this. So for the cathode we are having, so we are having that, then we are going to have plus 5 electron, then 8 that, then it's going to be that, then it's going to be 2 plus, so that's a 2 plus water. Okay, great. So that's our what? So that's our cathode. You see, that's where reduction is, huh? Then for the anode, for the anode is chlorate. Okay, so now that's pretty much about it. So now when you look at this, of course, when balancing, you multiply the first equation by 5. Oh, sorry, you multiply the first equation by 2, then the second equation by 5, so that your electrons, you have 10, then the electrons can cancel, then the water molecules will cancel. But anyway, we've already done balancing these equations. Where the money really is now is on writing these equations. So first of all, I'm sure you've taken note that up to now we are not writing electrons, right, in our line notation. So when you're doing your line notation, you don't you see we've not been writing electrons, huh? So now how we are going to write this, so we know that this is our anode, right? So we know we always start from the anode. Now, before we start from the anode, we know that here we don't have anything that can act as a what? Which can act as a metal. Okay, because they are all in aqueous, aqueous, aqueous. So there's nothing that can act as an electrode. Let's put it that way. Okay. So then what you do, then you use platinum. So what you're going to do is to show that the electrode is platinum. You open your line notation with saying platinum solid, meaning platinum is the metal that is what, that is acting as the electrode. Okay, then what then you do is you then put now this line to say, okay, now I'm done talking about the electrode. Now let me now talk about the actual reaction. Sorry about that. So let me now talk about the actual reaction. So now you then go now to the anode, and how you do it for the anode is, remember that like we've been doing it, you always start from what was first. Okay, what came first was this one, so you just write that one. Okay, and remember you also include state symbols, huh? Okay, but now Now this is what's interesting. So anything that's aqueous, we are going to include it. So now what then followed? What followed was this, right? So you write that. But how do you show, since it's the same, it's the same, uh, it's still the anode you're looking at, so you just put a comma. Okay, so maybe that comma is a little bit exaggerated, so you put a comma there, then you write that. Okay, then comma, then what else is in aqueous is that hydrogen, right? So you want to write the hydrogen, and I'm sure you've taken note that I'm not writing the coefficients, right? Like the numbers that are in front of these balanced equations, because like I said, you multiply this by 2, so it should actually be 2 there. This one should be 10, this one should be 16, this one should be 2. So anyway, we know we did how to balance, huh? This one should be 5, 5, because you're multiplying by 5. This one should be 10, then this one should be 10. Then the electrons can cancel. Anyway, we did that. So but just take note that I'm not writing those coefficients. And that's what I wanted to point out. So meaning that after you've exhausted, so you've now exhausted the what? You've exhausted this, you've exhausted that, and you've exhausted the hydrogen there. Things that were aqueous, that were in aqueous, you've exhausted them. So meaning that your what? Your anode is done. So what do you do to show that your anode is done? You put these to show either it's a salt bridge or a porous disc. After you do that, so meaning you've now left the what? You've left the anode. You're now looking at the cathode. So we're now concentrating on what? On this equation. So since we're now concentrating on that equation, what then you're going to do is you say, okay, so what started, what came first? So if you want, in this case, you'd say, okay, let me just okay, so depending on how you may have written your equation, but if you want, you may say, okay, let me put the hydrogen ions. Okay, but of course, yeah, of course, we are putting the hydrogen ions just for some sort of uniformity, anyway. So that from hydrogen ions. But anyway, that's about it. Now, for this one, now we have to follow how that reaction is. What started first? So what came first here was what? Was this one. It was this one which was what? It was this one that underwent the reduction to this, isn't it? So it was this one which was reduced. So you start with what was reduced and then you end with the end product. Same thing for the anode, you start with what was oxidized and to the end result, okay? To the end result. So what was reduced was the what? Was this. Then again a comma. Then what was the resultant? That was the resultant. So then what do we do then? Then we are done with the cathode. Now remember, do we have any metal here? No, we don't have any metal. So meaning what was acting as the electrode? As the electrode, platinum solid. So then you've done the line notation when none of the when the components don't have something to act as a metal or to act as an electrode. So that's pretty much about these line notations. Very, very important. They like them. So just before we can look at let's just summarize what we've discussed. So description of a galvanic cell. A complete description of a galvanic cell usually includes 4 items. So the cell potential, always positive for galvanic cell, where the so you've got there the cathode minus the anode and the balanced cell reaction, direction of electron flow obtained by inspecting the half reactions and using the direction that gives a positive E cell. Then you have to designate the anode and the cathode. Then the nature of each electrode and the ions present in each compartment. A chemically inert conductor is required if none of the substances participating in the half reaction is a conducting solid. So those are things that we've pretty much exhausted there. Okay, so now let's look at, so this example, I think we won't, I'll just explain through, since these are things that we've already done. So I won't write, I'll just explain them. Yeah, but there are things that we've done already. So I think just an explanation running you through how the calculation was done, I think it will be enough. So how do you describe this particular cell? So you're asked to describe this cell. So first things first, what are you going to start looking at? So we are looking at example 18.4, right? So how do you start? So first of all, they've given you those reactions. You have to determine from that to say which one is going to be the anode, which one is going to be the cathode. So you know what we say? The one which has got the E value, which is more positive, is going to be the what? Is going to be the cathode. So from there, you can tell to say, okay, the first equation is going to be our cathode, right? So meaning the second one has to be what? Has to be rotated. Oh, no, not rotated. Has to be reversed. Okay, so we have to reverse that one because we have to reverse the second equation because it's the one that's going to act as the what? That's going to act as the anode. Is everyone clear with that point? So it's the one that's going to act as the what? That's going to act as the anode. So that's why we have to reverse it. So meaning the sign of the sign of the E is going to change, isn't it? So that's something important. So having done that, so then of course once this is something we've already done, so you're going to see that your cathode there is your cathode, that's the same, but the anode has been reversed. Then you, it's almost like you're adding them. So I'm sure you may be wondering between those two things, the two methods that I was talking about. So what this basically means is, you see, if you say the method to say the E cathode, we are adding, okay? So let's say if you say the the E cathode plus the E anode. So what you say is the cathode is what? I just want to clarify this. Someone asked yesterday. So we're going to have 0.8 volts. Then what's the anode? This is plus, so meaning that the anode, you've rotated the anode. So when you rotate the anode, it's going to be what? Plus, then minus, right? 0.77 that. Then you're going to have 0.03 volts. Okay, so that's how you go about it. Then the second method, then it's where you say, and that's the one which they are using in Zunda. So for this method, you are saying the E cell is going to be what? Going to be E cathode minus. So in this one, they've already done the reversing in this equation. They've already done the reversing for you. So you just simply plug in your values. So negative, you just put in you put in the standard for the, so you don't they've already rotated, sorry, they've already reversed the what's this, the anode for you. So you just put in the value as it was. So for this case, you just put in the same positive value which was there, or the standard one, okay? Because the equation in itself has already done the reversing for you. So you see that you get the same answer, right? So I hope we see how this is just the concepts there that we have to understand. Huh? Okay, great. So since we've done that, then we can now proceed. So now after you've done this, then you're now asking yourself, then how do we balance this? It's already, the electrons are already balanced. So this simply means that electrons are moving from where? From their they are moving from ion 2, oh sorry, from ion 2. uh, the electrons are moving from ion 2 to go to the silver ion to form the what? To form the silver solid. Okay, so we are now explaining this. So after you've done this, then now you can realize that okay, so the one that's providing the electrons is the ion, so it's going to be the what? The anode. Then the one that is receiving, the component that's receiving electrons is the what? It's the cathode, right? So you know that where that ion, that silver ion is, that's receiving the electrons to become a solid. So you know that uh, it's what's this. So you know that that's going to be your cathode, right? So after you've done this now, you want now to write your line notation. So how do you write your line notation? Remember, you always start from the what? From the anode. So look at your anode. What do we have for the anode? The anode is the one where oxidation is occurring, right? And you see that this is the reaction where we've got ion. Now you see that the ion which we have, they are both ions. There is no metal. The best way you can tell is look at the state symbols. The two ions that we have, they are all in ionic form. There is nothing that is metallic. That's a solid that can act as what? There's nothing that is a solid that can act as an electrode. Therefore, in this case, what's going to happen is that for the anode, we are using platinum solid, innate, which is an innate substance, right? So we are going. So that's why you see that the line notation for the anode has started with what? Has started with platinum solid, because that's the platinum is the one that's going to be the electrode in this case. Then there you see the one that's being oxidized, then the resultant of the oxidation. Then you now go to the so you've got that salt bridge or porous disc represented by those two lines. Then you've got now the silver ion. So you've got the silver ion that's then separated by that single line from the solid phase, right? So you see that that one doesn't have the platinum. Reason being, it's because of the what's this? It's because there is that silver solid that can act as an electrode. Okay, so that's really those are the key concepts on describing the galvanic cell. And I'm sure you've seen the reason why I didn't write was that's something that we those are the kinds of things we've been doing from yesterday. So now let's now look at cell potential, electrical work, and free energy. So remember, the reason why someone made a battery is so that it can do work, right? So that it can power our phones, it can power vehicles. So you always want to get energy from these electrochemical reactions. So then, how does this work get done? So what we can do is that the work that can be accomplished when electrons are transferred through a wire depends on the push or the thermodynamic driving force between the electrons. So remember, we talked about how electrons are going to move from the anode to the cathode, right? And we know that that push, that's providing the push for the moving of the electrons is what we call the electromotive force, right? That's the electromotive force, okay? And it's defined it's defined in terms of a potential difference in volts between 2 points in the socket. So, or in the circuit. So basically, when you talk about electromotive force, you are basically saying between these between these 2 points uh, in my circuit, the anode and the cathode. What's really the difference in their volts? Then that's going to give you the what? That's going to give you the electromotive force. Okay, so remember we discussed that a volt is equal to, or rather it's the same as joule per coulomb. Okay, and that's what it's just showing there, that equation to say electromotive force is equal to potential difference, which is the volt, and we know the volt is equal to joule, which is the same as work over charge, and charge having a having the unit of coulomb. Okay, so that's about that. So how we are going to be, how it's viewed in this book, and because this book is your recommended book, so it means that's what your syllabus wants you to look at it like. So in this book, work is viewed from the point of view of the system. So what this simply means is that, you know, we are looking at work and saying, okay, what is this work doing to the system? Is it adding to the system, or is the system losing this energy? So that's why we use a negative sign. This simply means when you charge your phone, right? And your battery is keeping your phone on. What then happens is that because the battery is keeping your phone on, it's simply because energy is being sucked out of the battery, going to your phone to supply the phone, isn't it? So what then happens that we indicate that work done to be negative, or it's going to have a minus sign. That minus sign is simply saying that the system of the battery, or the battery, is losing energy. That makes sense, right? Okay. Then so that's why it's negative there, right? Then when a cell produces a current, the cell potential is positive. And remember, we've been talking that usually for a galvanic cell to be able to work, usually for it to even proceed, and we talk about predicting spontaneity. You will see that we always want to ensure that the cell potential is what is positive. Okay, so that's something that's important. So from this we see that the work is going to have a minus sign, where the cell potential is going to have a positive sign. So now when we know, we said that electromotive force, okay, let's just say for the E, which of course we know that the cell potential is pretty much going to give us really the electromotive force that's happening, because it's given in volts, right? So meaning that its electromotive force, or volts, is equal to work. That was the joule there. That was the joule for the work. Now the work, we know, is going to be minus, right? And for the reason that I've explained, then overcharge. So the charge there, charge has to be positive. Yeah, so that's the charge there. In Yeah, so that's the Q there. So really, that's really the key thing that we have to take note of. Now, the other thing that we have to take note of is the fact that when current flows, we know that energy is going to be wasted. And I gave an example of when you are ironing. You see that when you are ironing, depending on the kind of iron that you are using, some irons you may find that the cord, the cable, may get so relatively soft. You get my point, right? Because of the heat that's being reduced. And so that's why usually it's not possible for you to ever get the maximum amount of energy that a potential reaction is able to give you. And this is simply because of the losses which are going to be happening in real time. However, even though we can never achieve the maximum work through the actual discharge of a galvanic cell, we can measure the maximum potential. So what we are measuring basically is the maximum potential, meaning assuming if there were no losses, this is the amount of what? This is the amount of work that this cell can be able to do. I'm sure you may resonate that when your battery is about to get damaged, it usually starts to overheat, right? But when it's a good battery, you find that even though it may get heated, but it won't be at the same pace as a battery that's getting damaged. And you know that when a battery starts getting warm, heated, usually you realize that even its ability to stay for long hours will be reduced, right? So that's an important point to take note of. So then, even though we can never actually realize the maximum work from a cell reaction, the value for it is still useful in evaluating the efficiency of a real process based on the cell reaction. For example, suppose a certain galvanic cell has a maximum potential at zero current. So what does that mean? They are simply saying that at zero current, it simply means there is no current that's flowing, and because there is no current that's flowing, it means that no energy is lost. Because no energy is lost, it means that that value that they've gotten is the maximum potential, or it's the maximum electromotive force that that particular galvanic cell can produce. Huh? So let's take note of that. Hello, hello. Can everyone see my page? Oh, my. Can everyone see this? Hello, hello, hello. Can you hear me? Hello, can you hear me? People, can you hear me? Hello, can people hear me? Hello, 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 hello. Can you hear me? Hello, 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 hello. Okay, I think we may have had a challenge maybe with the network, but are you able to hear me? Hello, 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 Peep. Oh, yes, yes, you can hear me. Okay, okay, okay. I think that there was just an issue with my network. I don't know why I'm having challenges with my network today. Sorry about that. Let me begin. Okay, okay. So sorry about that. Okay, so sorry about that. I think there was a problem with my internet connectivity. I don't know why, but I seem to be having a challenge. Can everyone hear me? Okay. Yeah. So once again, I'm really okay. Sure. So I'm really sorry for that. Once again, I don't know what's happening with my internet connectivity today, but let's not waste any time. So we've already lost some. So let's just go direct to what we're talking about. So uh where were we? Yeah. So yeah. So that's okay. Trying to ensure that I record this anyway. Let's see how much we can be able to do. So yeah. So basically, there the context that we are looking at is that even though we can never really hello. Okay, I think there's some feedback. Okay, let's do this. Okay, can everyone hear me? Okay, great. Yeah, so even though we can never really actualize the maximum weight or the maximum work from a cell reaction. Okay. I think I'm back online. Let me mute this one. Okay, great. So sorry about this, huh? Okay, yeah. So even though we can't really, we can never, we can never actually realize the maximum work from a cell reaction. Yeah, the value for it is still useful, and we already talked about this, the maximum. So that's the maximum that we are talking about, right? Then in a particular experiment, 1.33 moles of electrons were passed through this cell at an average actual potential of 2.10 voltage. The actual work done is, so you can say work is equals to minus charge. Okay, so you can say the work is equals to minus charge times what? Times the E. And this is just basically coming from this equation there. The equation that's on top there. So you're just making work the subject of the formula, right? So that's something important to take note of there. So then, where we know that E represents the actual potential difference at which the current flowed. So again, you are looking at E is the actual potential difference, right? That actually was occurring, or that was actually happening in that particular cell. So that's something important to take note of. And then Q is the quantity of charge in coulombs. So remember, Q is this is the amount of charge, right, that was passing in that cell at that particular moment. So now the charge on one molecule of electrons is a constant called Faraday. So what you're basically looking, we know that electrons are going to be a lot, right? And so you can't count to say one electron, two electron, three electrons. So like we were doing for stoichiometry, we look at them as in terms of moles, isn't it? So then there was a scientist called Faraday that actually calculated the amount of charge that one mole of electrons, yeah, are going to be conducting, okay? And then he found that value, which we call now the Faraday's constant, okay? So he found that actually one mole of electrons is going to have 96,484 coulombs of charge. So what this means, the importance of this is that we can actually use this value to actually find out what amount of work a certain cell can do simply by looking at the number of moles of the electrons which are being transferred, right? So that's a very very important concept there. So that's Q. So Q, we know what Q is, the charge of the quantity of charge in coulombs, right? So meaning if we've got Faraday's constant, which is giving us the what? The charge on one mole of electrons, meaning when we multiply Faraday's constant times the number of moles, we actually get the charge that those number of electrons are what? Are going to have. And so this is what basically the first mathematical calculation is showing. Don't worry, we'll look at examples and we'll be able to calculate these things. But I just want to explain so that we can get a good perspective of this. So yeah, so you see, for us to get charge, Faraday tells us to say a mole of electrons is going to have what? Is going to have 96,484 coulombs of charge. So then we're thinking, okay, so meaning when we multiply that by the number of moles, then we can actually figure out the amount of charge that those moles are what? That those moles are going to carry. It's almost the same as if we were to say, let me just put it into context. I think it's going to be helpful. So how we could put this is, imagine if we say one mole of electrons is equal to 96,485 coulombs, right? Then we say, uh, then we've got 1.3 moles of electrons. Then we are just asking what will be the charge. So what do we do? We are going to multiply the what? The number of moles here. So what we are going to do is we multiply the number of moles here times the what? Times the Faraday's constant, isn't it? So that's basically, and then we'll be able to find this as our Q. Okay, so that's basically what's happening in this reaction. And so this particular equation is very, very important because we can actually be able to find out. Okay, so because we were disturbed by a minute or two, so we'll just give me about a minute, and then we'll be just to make up for that uh, uh, discontinuity that we had there. So yeah, so you see, so that's why this particular equation is important. So now remember, we are trying to find the work that this cell can do. So you know the formula for work is what? Is W is equals to minus Q and E. So we've been able to what? We've been able to calculate okay, let's just solve this together. So remember, we're trying to find the work, isn't it? So we're trying to find the work that can be done by this particular cell. So we know that it's going to be work is going to be minus Q and E. So we've already found our Q, to say Q is going to be number of moles times Faraday's constant. And I explained why we're doing this. So we're going to have that 1.33 moles electrons times Faraday's constant. Okay, uh, Faraday's constant. Okay, so you cancel those moles. So you're going to have a value there, right? So you're going to have a value. So you're going to say 1.33 times 96,485. So we've gotten our Q. So we've gotten our Q there, right? Which is going to be coulombs of charge, right? So we've gotten that. So now, meaning now, we can now find our work, right? And we told, and they told us that the E that was found was actually 2.10 voltage, and we know that this is the same as 2.1 joules per coulombs. Why am I using joules per coulomb? Because so that coulomb can be able to cancel, and we can have, because when we write joules, it will be relatively tricky for us to see the cancellation. Yeah, but it's basically the same thing. So we're going to write our Q the charge there, then times E. We're almost done. So then we are going to have, so that cancels, right? So I hope you're able to see uh, why I changed the why I preferred these units. And then don't forget the negative here. So you're going to get what? Negative 2.69 times 5 and joules. So then what does this tell you? So uh okay, so we'll look at the maximum work that can be produced. So what we are looking at here is the what? Is the actual work that that this particular cell did. So next time we'll look at the expected, and then we can be able to find the efficiency. So, but the take home point is that I hope you've been able to see and appreciate just how important Faraday's constant is in this. So, otherwise, thank you so much. I don't know.